Welcome back to the micromodule series, Understanding Bias in Epidemiological Studies. In this module, we will be focusing on mechanism and examples of confounding bias. The objectives of this module are to introduce the definition of confounding bias, explain the root cause of confounding bias, illustrate the consequence of confounding bias, and enumerate the methods for controlling confounding. So what is confounding? Let's look at a hypothetical example of smoking and lung cancer. Among smokers, the incidence of lung cancer is 1.4%, which is less than half of the 3.5% in non-smokers. At first glance, this seems to suggest that smoking can reduce the risk of lung cancer, which contradicts our common sense. A closer examination of the data reveals that most smokers are young, while only about half of non-smokers are young people. As we all know, old people are in general at higher risk of various diseases, including cancer. Therefore, it is possible that the lower incidence of lung cancer in smokers is partially or totally a result of the younger age of that group. In other words, the potential effects of smoking and age on risk of lung cancer are mixed in this example. Without removing the impact of different age compositions, it is hard to draw a reliable conclusion about the association between smoking and lung cancer. This phenomenon is called confounding in epidemiology. Confounding is defined as a situation in which the effect of exposure or association between exposure and outcome is distorted by the presence of another factor or variable, which is referred to as confounder or confounding factor. To put another way, the observed association of exposure with outcome is not purely caused by the effect of exposure, but a mixture of the effects of exposure and confounders. Therefore, to draw a valid conclusion regarding the association of exposure with outcome, it is crucial to identify potential confounders and remove their effects. To determine whether a suspected factor is a confounder, we need to evaluate it against the following three criteria. If it meets all the three criteria, it can be considered a confounder. Number one, the suspected factor should be a determinant, whether a risk or a protective factor of the disease, according to current knowledge. For example, when examining the association of smoking and stroke, age fulfills this criterion because older age is a well-established risk factor of stroke. Number two, the suspected factor should not be an effect of the exposure. This means that it should not be part of the causal pathway from exposure to outcome. For example, smoking does not cause someone to be older first before it eventually causes stroke, which means that age is not part of the pathway from smoking to stroke. So age fulfills this second criterion too. Number three, the suspected factor is associated with exposure. This means the distribution of the suspected factor differs between the exposed and non-exposed groups. For example, if the mean age of smokers is 48 years and that of non-smokers is 64 years, which are very different from each other, it would suggest that age is imbalanced between the two groups. This diagram illustrates the relationship between exposure, outcome, and confounder. The suspected factor should meet all three criteria to be a confounder. Otherwise, it will not be a confounder. Number one is that the third factor should be a determinant of the disease. It may increase or decrease the risk of outcome. Number two is that the third factor must not be part of the causal pathway from exposure to outcome. Number three is that the third factor should be associated with exposure, or in other words, imbalance between the exposed and non-exposed groups. Whether the suspected factor fulfills criteria A and B are judged based on prior knowledge, common sense, or biological reasoning, rather than based on the data or analysis of our own study, which is being conducted. However, we do need to use the data collected from our own study to test criterion C, that is whether the suspected factor is imbalanced between exposed and non-exposed groups. If there is no such imbalance, the factor cannot cause confounding bias to the results of our study. Therefore, the root cause of confounding bias in a particular study is that some factors that fulfill criteria A and B are imbalanced between the comparison groups. Now let's come back to the example of smoking and lung cancer. In this example, the root cause of confounding by age is the imbalance of age distribution between groups. If age were well balanced, it would not cause confounding because the difference in risk of lung cancer between the two groups can by no means be attributed to age in this case. Confounding is important because it distorts the effect estimate that measures that association between exposure and outcome. If not adequately controlled, it may lead to inaccurate or even totally wrong conclusions. Again, let's come back to the example of smoking and lung cancer. According to the information given in previous slides, the incidence of lung cancer is 1.4% in smokers and 3.5% in non-smokers. Comparison of these two will give a relative risk of 0.4. Based on this result, we will conclude that smoking is a protective factor for lung cancer. However, if we look at the situation in old people and young people separately, we can see that the risk ratio is 1.5 in both groups, indicating that smoking is a risk factor for lung cancer. So, confounding caused by age could lead to a completely wrong conclusion in this example. Whether examining the existence of confounding, it is important to bear in mind that as long as the third factor meets all the three criteria, any difference between the adjusted and crude effects would indicate the existence of confounding. The magnitude of the difference is a matter of whether the confounding effect is large enough to be important, but not whether the confounding effect exists. The so-called rule of thumb, using a difference of 10% or 20% as the threshold for defining confounding, is not justifiable because the magnitude of difference is related to many factors such as sample size. There are 6 commonly used methods for controlling confounding, including restriction, matching and randomization, which are used in the design stage, and stratified analysis, standardization, and multivariable regression analysis, which are used in the analysis stage. The rationale of these methods is the same. All of them attempt to make the exposed and non-exposed groups comparable in terms of the distribution of suspected factors. By doing so, there will be no or minimum imbalance of these factors between groups, hence removing the root cause of confounding. These methods will be introduced one by one in the following modules. Of note, we don't need to use all these methods in every single study. The choice depends on the study's objectives as well as feasibility. Okay, in this module, we discussed the confounding bias arising from imbalance of the third factor between exposed and non-exposed groups, the consequence of confounding bias, and the strategies to mitigate it. In the next module, we will talk about the use of restriction and matching for controlling confounding. Thank you for listening.